Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. Let us have some exercises about the first two parts of section 4.3. So about intervals of increase and decrease, and local maximum and minimum values, and intervals of concavity and inflection points. So we know now that to find intervals of increase and decrease, which is part A, we need to deal with the first derivative. So the first derivative is 4x to the power 3 minus 4x. Now the intervals in which the first derivative is positive, the function would be increasing. The intervals on which the first derivative is negative, the function would be decreasing. So if we take 4x as a common factor, we will have x squared minus 1. And if we put it equal to 0 to find the zeros, we find that x is 0, this is one of the zeros, and x squared equals to 1, so x is plus or minus 1, square root of 1, which is 1. So there are three zeros of f prime. So we make the table of f prime. Here negative infinity, here negative 1, 1, and infinity. Now look to f prime. This is f prime. Okay, it is exactly equal to this. If I replace x by 0, I will have negative. Oh, 0 is also 0 is also a 0, so I have three zeros. If I replace x by 0, actually I get f prime 0. So choose a number greater than 1, 2, for it would be positive. And because you can write f prime as this, and f prime is of degree 3, and it has three zeros, so each one of them has multiplicity 1, so the signs would be alternative. And you can check that by choosing any sample numbers. So if here is decreasing, if here is increasing, if here is decreasing, if here is increasing. So f is increasing on the intervals from negative 1 to 0, union 1 to infinity. And f is decreasing on the intervals negative infinity to negative 1, union 0 to 1. And we can see that at negative 1, we have local minimum. So the local minimum is actually f of negative 1. And we can find f of negative 1 by replacing x here by negative 1. So it is 2. So the local minimum is 2. And also there is another local minimum. So there are two local minimums. F of 1 is also a local minimum. And if you replace x by 1, you get also 2. While the local maximum is f of 0. And f of 0 is 3. So we answered part A, and this is also the answer of part B. So actually we answered parts A and B. Now part C, to find the intervals of concavity and inflection points, we know now that we have to deal with the second derivative. So this is the first derivative. and the second derivative is 12x squared minus 4. If I put it equals to 0 to find the zeros, I can take 4 as a common factor. So 3x squared is 1 and x squared is 1 over 3 and x is plus or minus 1 over square root of 3. So I make a table for f double prime, study the signs of f double prime, and I have negative infinity here, negative 1 over square root of 3 and 1 over square root of 3 and infinity. Now, if double prime is degree 2, the coefficient of x squared is positive. So between the zeros, the sign would be negative. You can always check by taking sample numbers. So if here is concave up, here it's concave down, here it's concave up. So f is concave up on negative infinity to negative 1 over square root of 3 union from 1 over square root of 3 to infinity. And f is concave down on the interval negative 1 over square root of 3 to positive 1 over square root of 3. And we have two inflection points. One of them is negative 1 over square root of 3 and f of this. And we can replace x in f by this number to the power 4 minus 2 times to the power 2 and plus 3. And the answer is 22 over 9. And also another inflection point at 1 over square root of 3. And if you replace x by this number, you will get the same y value because actually this function is even function. So this is the answer of the question. Another question. Well, for part A, I need to find f prime. And I have to use the quotient formula, the quotient rule. Derivative of x is 1. Derivative of the denominator is 2x times the x in the numerator. So I'll have 1 minus x squared minus 2x squared is minus x squared. So I have 1 minus x times 1 plus x. It's clear that f prime, the denominator of f prime is always positive. So, and there are two zeros, either x is 1 or x is negative 1. And between these two zeros, f prime has degree, not f prime, the numerator, which controls the sign of f prime, because the denominator is always positive. The coefficient of x squared is negative 1. So here the coefficient would be positive. If you replace x by 0, you can immediately notice that f prime is positive between -1 and 1. So it is decreasing, increasing, decreasing. And part A would be f is increasing on the interval -1 and 1, and f is decreasing on the interval from -infinity to -1, union from 1 to infinity. And for part B, we have a local minimum. The local minimum actually is f of -1, and that would be -1 over 2, and the local maximum would be f of 1, and it is 1 over 2. So this is the answer of part A and B. Now let us answer part C by finding f double prime. Well, I will use this one. Using the quotient rule, and the derivative of the numerator is -2x times the denominator minus the numerator times the derivative of the denominator using the chain rule. And to simplify f double prime, I will take common factors from the numerator. So how many terms are there in the numerator of f double prime? 2 terms. This is the first term, and all of this is the second term. Well, what do we have? I have 2x, -2x actually in both terms. And I have x squared plus 1 in both terms. Even in the first term, it is to the power 2. So now, from the first term, it's left only x squared plus 1 is left, not taken. And notice that this minus is taken, so it would be plus 1 minus x squared is not taken, and there is a 2, so it's actually plus 2. X squared plus 1, okay, 2x, okay, the minus sign is okay, so that's it. Taking common factors will make your life easily in simplifying. So I can cancel x squared plus 1 with one of the x squared plus 1 below to have x squared plus 1 to the power 3 in the denominator. And here I have 1 plus 2, that's 3. And x squared minus 2x squared is negative x squared. Well, notice that the denominator is always positive, x squared plus 1. So the zeros of f double prime comes from the numerator. X equals to 0, this is a 0. And x squared equals to 3, or x is positive and negative square root of 3. So these are 3 zeros of f double prime. Let us test the signs of f double prime. Well, notice that I have 3 zeros, and the numerator of f double prime is of degree 3. So it's enough to find one sign in one interval. So I'll take a number greater than, well, let me take 1. 1 is between 0 and square root of 3. So if I replace x by 1, this would be positive and this would be negative. So f double prime would be negative. So it would be positive here, and negative here. So if here is concave down, concave up, concave down, concave up. So now part C, uh, F is concave up, okay, on negative square root of 3 to 0, union square root of 3 to infinity. And it is concave down from negative infinity to negative square root of 3, union 0 to square root of 3. And inflection points, I have 1, 2, 3 inflection points. So I have negative square root of 3 and f of negative square root of 3, which is negative square root of 3 over 3 plus 1, 4. Another inflection point, that's square root of 3 over square root of 3 over 4. I'm replacing x by this number in the definition of f of x. And if you put x 0, f of x would be 0. So these are the 3 inflection points, and this is the answer of the question. Another example or exercise. Well, let us find f prime. I need to find the zeros of f prime. So let me add these 3 terms. So I have x, here 2x squared minus x minus 1. So let me try to factor the numerator. So yeah, this factoring is correct. So I have f prime now. Notice that the domain of f, because we have len x, is from 0 to infinity. So the zeros of f prime, I have x equals 2x plus 1 equals 0, so x is negative half. But this does not belong to the domain of f. I have x equals 1 and x equals 0 will make f prime does not exist. But this does not belong to the domain of f. So to answer part A, I make a table for f prime. And now this table starts actually from 0. So now this is 0 because the domain is from 0 to infinity. And I have only 1 here. Negative half is not in the domain. 0 is not even in the domain. So if I take a number, so the sign, notice that from 0 to infinity, 2x plus 1 is positive. X is positive. So everything depends on the x minus 1. If I choose 2, it would be positive f prime, of course. And if I take 0 half, f prime would be negative. So here the function is decreasing and the function here is increasing. So the answer to part A, f is increasing only from 1 to infinity. And f is decreasing only from 0 to 1. And for part B, I have local minimum, but there is no local maximum. F of 1 is a local minimum. And if I replace x by 1, 1 minus 1 minus ln 1, that's just 0. So f of 1 is the local minimum. To find C, I need to answer C, I need to find f double prime. And to find f double prime, it's easier for me to work with this one. I don't want to use the quotient rule. So the derivative of 2x is 2, derivative of negative 1 is 0, derivative of 1 over x is negative 1 over x squared, and there is a negative here, so it's positive 1 over x squared. I can add these two terms. And I can see from here that this is positive and this is positive, so f double prime is actually always positive. It will never be 0 even. It's always greater than 0. And this means that f is concave up on all the domain, which is from 0 to infinity. The domain from 0 to infinity, always concave up. And no inflection points because concavity does not change. Another question. Let us find f prime. I use the product rule. So f prime is 2x ln x plus x squared over x is just x. Well, to find the zeros of f prime, let me take x as a common factor. So I have 2 ln x plus 1. If I put it equals to 0, then I have x equals to 0. This is one answer. And 2 ln x equals to negative 1. And ln x is negative half. And x is e to the power negative half. You raise both sides to the base e. Well, again, we have to pay attention here to the domain of f. We have ln x. So the domain of x is from 0 to infinity. So this 0 does not belong to the domain of f. Now, what is e to the power negative half? It's a positive number because e cannot be negative, e to the power x. It is approximately 6.61. So it's a positive number and it belongs to the domain. So that's the only critical number. Well, we don't start from negative infinity here because the domain does not start from negative infinity. The domain starts from 0. Of course, if the domain is from 0 to infinity, then everything is from 0 to infinity, increasing, decreasing, local minimum, local maximum, everything. There is nothing to the right, to the left of 0. Okay, f prime. If I choose a number 10, for example, where is f prime? This is f prime. If I replace x by 10, ln 10, everything is positive. If I replace x by less than this number, 0.1, for example, you will find that ln 0.1 is negative. And this will make 2 ln 0.1, okay, plus 1 would be a negative number. So this is negative, and if here is decreasing, if here is increasing. So the answer to part A, f is increasing on e to the power negative half to infinity, and f is decreasing on the interval from 0 to e to the power negative half. And the answer to the part B, we have a local minimum at 0.61, or the local minimum is just f of e to the power negative half. And f of e to the power negative half would be e to the power negative half to the power 2, and that's e to the power negative 1 times ln e to the power negative half, and that's just negative half. So it's negative 1 over 2e, and I can approximate this number. It is approximately negative 0.18. Now, to answer part C, I need to find f double prime. And to find f double prime, which definition should I use? This one. Now, the derivative of, I use the product rule here. Derivative of 2x is 2. Derivative of ln x is 1 over x. Derivative of x is 1. Well, x cancels with x. And 2 plus 1 is 3. So I have 3 plus 2 ln x. Well, f double prime would be 0 when 2 ln x equals negative 3, or ln x equals negative 3 over 2, or when I take both sides to the base e, so x is e to the power negative 3 over 2. And I can check an approximation for negative 3 over 2. It is approximately 0.2. So let us find the signs of f double prime. And it doesn't start from negative infinity. It starts from 0 to infinity. The domain of f is from 0 to infinity. The number is e to the power negative 3 over 2. If I choose a number greater than 0.2, for example 10, then 3 plus 2 ln 10 would be positive, and I'll have negative here. So here f is concave down, here f is concave up. And the answer to part C would be f is concave up on the interval from e to the power negative 3 over 2 to infinity, and f is concave down on the interval from 0 to e to the power negative 3 over 2. And actually I have an inflection point, and the inflection point has coordinates e to the power negative 3 over 2 and f of e to the power negative 3 over 2. So if I raise it to the power 2, it would be e to the power negative 3, and ln of e would be negative 3 over 2. So that's why that's the inflection point. Another question. Let us find f prime. Use the product rule. Derivative of x is 1. Derivative of e to the power 2x is e to the power 2x times 2. Let me take e to the power 2x as a common factor. I have 1 plus 2x. When I put it equals to 0, e to the power 2x cannot be 0. So the only solution is 2x plus 1 is 0. So 2x is negative 1, or x is negative half. Of course, the domain of f here is all real numbers, so we have no problems. from negative infinity to infinity, and here I have negative half. Well, f prime, the sign of f prime depends on 2x plus 1. To the right of negative half, the sign is positive, and here it's negative. So decreasing and increasing. So the answer to part A, f is increasing on the interval from negative half to infinity, and f is decreasing on the interval from negative infinity to negative half. And part B, I have a local minimum, and the local minimum is f of negative half. And if you replace x by negative half, you will find it negative half, okay? And e to the power 2 times negative half is e to the power negative 1. So I can write it below here. So this is the local minimum. To find the local maxima, to find concavity, I need to find f double prime. Well, let me use this one. The derivative of f prime would be derivative of e to the power 2x is 2 times e to the power 2x plus, now I have product. Derivative of 2x is 2 plus 2x times the derivative of e to the power 2x, which is e to the power x times 2, so this would be 4. Now, what do we have? I have 2x plus 2e to x, 2e to x plus 2e to x, that's 4e to x to the power, plus 4x e to the power 2x. I have 4 times e to the power 2x as a common factor. So 1 plus x. Now if I put it equals to 0, 4 e to the power 2x cannot be 0. So the only 0 is x equals negative 1. From negative infinity to infinity, and this is negative 1. If you choose a number greater than negative 1, f double prime would be positive. So concave down, concave up. So the answer to part C, f is concave up from negative 1 to infinity, and is concave down from negative infinity to negative 1. And I'll have an inflection point at negative 1 and f of negative 1, which is negative e to the power negative 2. Or you can write it negative 1 over e square. That's it. I stop here, and I hope now you mastered the ideas of increasing, decreasing, and concavity.